So thanks, folks, for taking your time out of your busy weekend to hear me talk about firmware. So I'm going to reprise a talk we gave, I think, a couple months ago in Erlangen, Germany, at the Open Source Firmware Conference, OSFC. So OSFC was its first year, and it really is an outgrowth of the Core Boot conference. And so what we've observed in the industry is there's a lot of open source firmware. And really, this is firmware for booting, not necessarily like the embedded stuff like the free RTOS or what have you, or Zephyrs. This is really about boot firmware, so U-boot, Core Boot, and EFI style BIOS. And so what I was asked to give a keynote, and so really reprising that talk after attending the conference. I actually wanted to give other people's talks because they were more interesting, but I thought that would have been kind of weird. So figured I could speak at least first person to this content. I work at Intel Corporation up here in Bellevue, next to Microsoft. Started Intel in '97 in DuPont. They closed DuPont, moved us to South Seattle, closed South Seattle, moved us up here next to Microsoft. And I've been working on EFI for a while, but before EFI and Intel, sort of what got me excited about embedded was my father had given me an 8085 development board. It had a book with the ROM'd monitor, it had schematics, and there's the crappy board. I still have it, dug it out of my closet. And so back in the 80s, when you did embedded, you could sort of touch everything, especially from Intel. They published data sheets, they gave you source code, and you could actually put hands on hardware. These days with SoCs and third-party IP and people considering firmware to be more of a competitive, sometimes you really can't get your hands back on all the source code and really dig in and embed on embedded. And so that's what I'm going to talk about, is how in 2018 we're trying to get back to a world more like that. Can't claim we'll give you microcode listings and stuff, but you know what inspired me was really being able to touch things. I've always worked on embedded firmware, know what was happening down to the bare metal, and you know, really can we get back there with today's modern hardware? And you guys can break in anytime with questions or comments or minority report disagreement. But so Intel's view of this is, how do we approach this? I think simplicity is one thing. Things have gotten pretty complex over the years. The PC, when it started in the 1982 with the PCAT BIOS, was 8K of ROM. Today, to boot a modern system, you probably need 16 megabyte of code in the SPI-NOR between management engine, 6 meg of BIOS code. Things have gotten kind of complex. And then the point I mentioned on the earlier slide of openness. If you buy a board today, rarely can you get all the source code to initialize it. A lot of the data sheets aren't public. And then security. So there's business reasons why things have gotten more complex. We support more standards over time. The first PC, the ISA-bus, was the memory bus. There really wasn't memory initialization. Today, turning on a DDR4 controller probably takes 150,000 lines of C code. And then things aren't open because a lot of the IPs, but now we're faced with security where people want to know what's happening in a machine. Having a lot of opaque capabilities in a platform is a business concern, as much as with that much complexity, having third parties and communities to help develop things, helps with security. What did Linus Torvalds say? With open source, all bugs are shallow. So security is a good thing, driver for openness also. So this SOS, make things simpler, make them more open, and how do we address security are kind of the pillars that are motivating some of the things we're doing at Intel with the host firmware. So again, simplicity. We build pretty broad and complex code bases. We support, if you've ever read the Windows 10 logo, what it takes to the firmware requirements, there's probably 250 pages. There's thousands of pages of industry standards from the TCG, DMTF, USB, HCI. So we don't embrace complexity because we like lots of code. It's really the business requirements drive complexity. But really, we don't want the code base to express that complexity necessarily. Complexity is fine if there's a business reason, but make the elements that address those different complex components more composable. So that if you have a PC that wants to boot, MS-DOS all the way up to Windows 10, you maybe need all these capabilities. But if you're building a cloud server or an IoT device, maybe you only need to turn on your DRAM controller and jump into Linux and Flash. Intel wants you to turn on its CPU and its system on a chip, and if a customer only needs a subset of that code, make it such they can pull things out more readily. And if you're, again, the cloud provider and you're maybe get audited by what is your whole software stack doing, having less code has business value. It's not just aesthetics. Onboarding new people, say you're converting sockets from an ARM PowerPC to an x86, it shouldn't be have to get a PhD in firmware to figure out what to do. So simplicity is one of the first things we're doing. And then openness. Today, I think at CanSec West and Black Hat, we always would show this picture of the supply chain where we have some open source, but we have some closed source trees, BIOS vendors. And so really, we've realized with the supply chain, so many people need to play open source is really imperative. And so we have a lot of history at Intel. We're one of the largest contributors to the Linux kernel. So move that way to sort of IA firmware. And so through the EDK2 project, TNO Core, a new project we started, the Slim Bootloader, we contribute to the Core Boot project, is really have openness all the way to the stack. And depending on which of the firmware technologies you use. And then one of the other talks at OSFC, that conference in Germany, was from our team in Ireland doing audio firmware. So a lot of modern SoCs have a DSP in there to do audio, all the verb processing and such. And so opening up the firmware to that. There's a project called Open BMC, opening up the firmware on baseboard management controllers. And there's other parts of the SoC we'd like to open the firmware up. Because on a modern system like this Surface device sitting in front of me, the BIOS is one executable component. It runs on the host CPU, but there are probably 16 other reprogrammable elements. Your storage controller, your network adapter, your touch controller, your TPM has updatable firmware. So I think there's quite a bit. And so we really want to open up the host firmware. And part of the business reason for that is when people are adapting our SoCs for their own platforms, they need to change some of that host firmware. But correspondingly, whether they need to change the SoC firmware, the device firmware, or just want to see what's happening for security assurance, the path isn't just to open up the BIOS itself. But since I'm a BIOS guy, I'll talk more about the host firmware. Go ahead.
You mentioned OpenBMC. What's the brand name for the audio firmware open source thing?
I think it's the Open Audio. I don't recall. I'll send you a mail. But it's if you go to the OFC.io website, his talk is linked off there. But yeah, we definitely want to open up more components. So yeah, openness is one pillar, and then the final is security. I always counterpoint my earlier quote from Linus that all openness makes bugs shallow. Look at the OpenSSL project. It was open, and one guy was working on it, and it was a bug farm. So it's a necessary but not sufficient condition. But what we really like is openness during our design, development, deployment. And one of the things we do in EFI is a lot of our security critical code that's not NDA, doesn't read on the hardware, we open source. And we get a lot of feedback from the different OEMs, researchers, and I think that's great. Initially, people thought, hey, why are they telling us all these bugs? Why are they picking on us? And you have to remind people, when they're telling you about the bugs, those are the good guys. The bad guys found the same bugs and they're not telling you. So open source really helps, openness really helps with security. And then simplicity. If the code is so complex, a security subject matter expert can't figure out what you're doing, then you really don't appreciate the input of that community. So progress, since I was given the keynote, I didn't go deep in anything really. I just wanted to give a peekaboo on some of the things we're doing, and can go deeper on the Q&A or point to other stuff on the web. So one of the things we're doing is evolving this thing we have called the Intel Firmware Support Package. And so historically, the Intel initialization code is under NDA, only given to certain companies that need to build platforms, and really can't open source it all today. So we built a sort of a well-formatted binary that hides some of that IP-protected code, but put it on the web. So you drop this binary blob into your platform and wrap it in open source code. And the open source code we're really driving new progress in is this Slim Bootloader. It's something more like Core Boot, but it's made out of EDK2 source code. It's permissively licensed with the BSD, so you can do what you want with it and not have to give it back. And then something called the Min platform architecture. And so one of the things we observed is when you build an EDK2 based product today, we have 2 million lines in open source, probably some multiples of that in closed source. And so when you build a product, you may pull 300,000 lines of the C code out of the open source, maybe 250,000 from the closed source. And we had this one closed source package called Platform Package. It does everything for the silicon outside of FSP. Out of those 100,000 lines of code, we really only needed 20,000 or 10,000. We found those 20,000, we've open sourced them. So we have a recipe. You can take an open source BIOS core on EDK2, an FSP, and this Min platform code and build a product. Now it may not have all these fancy weird features, but it's enough to turn on memory, boot your OS, and enough to get your Windows 10 logo check off even. So that's what we're doing on Simple. Have a recipe for this stuff. You don't need a PhD in firmware. And then having embodiments of it for different platforms. So essentially for each of our lines of business today, Intel really is a server, IoT, and client. Client would be like this Surface in front of me, our big and small core, our i5s and 7s and 3s. Those are our client CPUs. IoT often derives from the client and server roadmap. It builds their own bespoke SoCs. So, and then server. And so what we've done is for Kaby Lake, that's our Gen Core i7, Core, I forget, 7th generation, 8th, I don't know what Kaby versus Coffee, but we have an open source version of that. We'll talk a little bit about the server we opened up, and then an Apollo Lake IoT. And then the sound firmware I mentioned that I don't know if I have the link in the deck here, but I can give you afterward. And then MicroPython. So again, UEFI is in C, it's great, but a lot of the world folks want to use dynamic languages, and so we're looking at upstreaming Python 3 conformant MicroPython for both testing and doing pre-OS applications. And then the final one, and if you want to know more on chipsec, you have one of the reigning experts in the room over there with Lee can talk about chipsec, but the gist of chipsec and his other half, Paul. So a chipsec is essentially a tool that runs pre-OS in Python or during the OS that has plugins that can tell you the security posture of the system. And then Capsule Update is one we're spending a lot of time on, which is really initially a mechanism that from the operating system you could send a well-defined binary payload into the platform to update the firmware. I think I have a slide on it later. I'll talk a little more, but it's more generally aligned with when I mentioned those 16 updatable firmware elements on a motherboard. How can we get automation and help people actually ensure that those things get updated? Because this is one of our grand challenges now is, say you built a platform with these 600,000 lines of C code. If people aren't servicing it, complexity actually becomes worse in the market and then the fact that a lot of people are using the same code base means it becomes something of a monoculture. So,
At the risk of putting you on the spot, I think I asked you about this privately, but a bunch of the tools for detecting Spectre Meltdown and the other stuff are standalone tools not integrated with chipsec and kind of disparate from each other because they were clearly developed by different groups inside Intel. So Spectre Meltdown, I forget all the other ones.
You mean
each
CVE detection
often comes out with its own tool.
oh, okay.
Maybe it wasn't you, maybe it was somebody else.
Yeah.
No, you were talking to Eric.
Oh, Eric at
That's
B-Sides,
right,
okay.
yes. So I was sort of complaining about it, but is there any thought to, I think what Eric said, to put him on the spot since he's not here, was that basically there's a lot of internal issues getting all that stuff synced up and aligned, so that there's just one tool that you can use for everything.
Yeah, it's very possible. I wasn't familiar with the AMT and the side channel tools.
Right.
And generally what we try to do is, chipsec sort of came from URI back in the 2014 and 15 when there were so many EFI exploits, we would publish a document and give people patches, but often people weren't applying them. And so ChipSec was a tool that for each new exploit, we'd have a plugin that can say, hey, platform, did you fix this specific issue? So as Legbacor, MITRE, URI, ATR would do all their conferences with all their new attacks, you could say this attack, that attack, that attack. We could say there's a ChipSec test for the ChipSec test. That's always been the intent, but sometimes when it's like a silicon issue, maybe the register that you have to check isn't in a public doc, so we can't put a public test to talk to a register, or for other reason. And we've never done destructive tests either. Like, we wouldn't put a test out there that would make a machine inoperable. So you won't see that class of tests in ChipSec either. But a lot of the ones Eric probably was mentioning were NDA constrained, I'm guessing, or just processed with other parts of the company.
He was talking about the publicly available Intel CVE 00086, that one, for example. It's a public CVE detection tool. It's a Python program. Oh. So here's ChipSec with this set of tests, and then over here is a separate one standalone that's not integrated.
Oh, that's just a door. And is
so there are 2 or 3 like that could be better.
And are the other ones open source?
They're open. Well, okay. So one of them is clearly all open source, top to bottom. They give you C that you compile, and then you run a Python wrapper for it.
Interesting.
The other one includes some binary stuff that there appears to be no source code, but I may not have found it.
Yeah, maybe if we could do I'll take
I'll
it.
follow up offline. Would be really good.
Yeah, sorry.
But that's a good one, and I think it hits the spirit though, and that's why questions like that are great, because this is the spirit of what we're trying to do. The tactics, like you just asked, it's one of the tactics. So no, I think it's a very fair question. It's appropriate. But I'm a firmware guy. I'm not a test guy, and that's where I stumble a bit on some of those test questions. But firmware options today is like a buffet. There's a lot of choices on how you can build your host firmware. And for folks that don't do firmware, where do we live in the world? So the reason we get a lot of attention is I don't think it's necessarily the best software, the most important software. But in the past, a lot of the attacks, Win32 heap exploits and other things, were all up high in the stack. It's pretty easy. You install an app, you can break something. You don't need admin access. The OSs and VMMs have been getting pretty good, and so people have been looking further south into the platform for some sort of soft points, and that's where host firmware has really come into play. But it's super privileged, whether it's ARM with Trust Zone, x86 with SMM. That's co-equal privilege to these hypervisors. It's often part of the root of trust for booting. And there's a lot of different efforts today. So I'm EFI guy. I've been on the EFI team since '99. It's a standard, and it's our EDTA2 code base. The Linux BIOS project started at the same time. There's Core Boot, U-Boot in '92, Linux Boot the last couple years. So there's lots of ways to do your firmware here. And then most of my talk today is this host firmware, but again, all these peripherals, these 10 devices, may have their own firmware in it. So that's why there's a lot of attention on firmware today, is as people are worried about security, posture of machines, and then you've heard all these talks on supply chain. When these things get manufactured and firmware gets sort of squirted in all these places, maybe some of it's opaque and can't even be ascertained the provenance at runtime. And so that's kind of why a lot of people are sweating firmware today. But again, the spirit of this talk and really what we've been doing in Intel is something really share with Google and the Facebooks of the world, where these web companies all grew up in open source. A lot of it's not philosophical. It's that how do you pool resources, and how do you go faster? So sort of trying to move the spirit of that openness into the host firmware space. So my sort of close here, what I'll do is give you a little more examples on some of the things we're actually doing with our open source. And so the first is, I mentioned that firmware support package. Again, a lot of this code in the middle is typically NDA, Intel, the documentation behind it and the code itself never goes on a public website. But you need this code to turn on parts of the CPU. Our system agent is where does our bridge to the rest of the system. Our memory controller PCH is like our south bridge, and then initialize our management engine. A lot of that code, you need it for a platform, to build a platform, but since it's not open source, someone building a platform out of open tools in open source core can't do it. And so we have this binary blob that you can put inside of an EDK2 style BIOS, a UEFI BIOS on the left, or core boot on the right. I mentioned that min platform. Some of the other code in the middle, that turquoise, was historically not opened. So we make that code open source because that turquoise code you often have to twist and turn based on your board design, your GPIOs, other things. FSP is just turning on silicon.
I was going to ask a question. Minimum SLID bootloader, you're expecting that to be used for the left side for Windows PCs, but not for core boot, right?
So this is our normal full meal deal UEFI. It'll boot Windows 10. This is how Chromebooks work. They have a payload where they put either depth charge. I think some guys are looking at putting Linux boot here. And a slim bootloader looks like this, except it has a phase 1, a phase 2. So the slim bootloader really looks like this picture.
But it's intended to be used on the left side for Windows OEMs and the right side for Chrome OEMs.
Right, and so the slim boot one, so this actually picture is a mimetic of a lot of what embedded people do. So people building like appliances like a router will often take this payload, instead of putting boot firmware, they'll put Linux directly. So cut off Chrome OS, say, and they might boot Linux right out of the flash. They just need enough code to turn on the silicon.
So definitely Linux or embedded Linux could use slim bootloader.
Yes, and that's the target.
And Chrome OS wouldn't use it because they have their own stack. What about the Windows side?
So the Windows side typically uses this because this has all the features. You can put EFI, as there's an EFI payload. So that's where the world gets really complicated. That Chinese buffet, some of the food spills between the bins. I don't have a better metaphor. That's really bad. That green code there is a lot of superstructure code that fabricates the EFI interfaces. You can take a subset of that and even put it here. And so you can boot EFI on a Chromebook and boot Windows. So at the Core Boot Conference in 2016, Ron Minnick held up, some high schooler had taken a Chromebook and put EDK2 on top of this code. So this code turns on silicon. The payload is really your persona on services for the OS loader. So the EFI spec gives you services like block, services reading the disk, talking to the console. It's things that an OS loader needs. You can put that here also. And so Slim Bootloader project also can have EFI as a payload. So you could boot full up EFI Linux. You possibly could boot Windows. I don't know if anyone's tried. So how you build the underlying platform initialization is kind of opaque to the OS. It should be, because the OS is parameterized by ACPI, UEFI. But this recipe is sort of the mainstream. It has all the features. This is what the whole PC server supply chain uses today on the left, the EDK2 solution. This one's embedded. And then what we're trying to do with these min platforms is make it easy to pull out green and turquoise pieces. So the difference between these solutions isn't complexity. It's a business choice. Maybe here, Core Boot is GPL2. So if you, as a vendor, added some code to RAM stage, say you built a super widget, and if you shipped the product and made a change here, you have to give up the code to your super widget initialization under the GPL2. If you did it with the EDK2, since it's BSD, you wouldn't. So maybe some people would choose one or the other because of IP concerns. Maybe you have a team that has been doing Core Boot for 10 years and loves it, or a team that's been doing EDK2 loves it. And I think my view is, at Intel, that thing at the bottom called hardware, just want them to be able to use it, right? I don't think we should be so partisan on how it gets done. But there is a world of a lot of people want to do things alternate ways, and so things like FSP are a compromise. And then the real challenge we have is how can we successively open more parts up of the FSP, and I'll talk about that in a few minutes here. But that's the gist on a modern system today. And so if you're an ARM system, this FSP is often replaced by something called a boot ROM, but they can cross-compile the same C code, this green part, this green H on the left, and like an ARM server for the generic EFI code cross-compiles, Linaro plays. They'd have their own platform-specific code. And so you can boot an ARM server on it, and correspondingly, ARM Chromebooks cross-compile the RAM stage, ROM stage to ARM, and the FSP is the ARM vendor-specific boot ROM, Or if it's a MediaTek device, they've open sourced everything so there's no blob. Like a MediaTek Chromebook is all open source. So, yeah. The 3288s and 3399s. And so, but the key is, and the reason we like standards like UEFI is, so OS vendors don't have to customize their kernel per different platform. Why is Windows, can you just download Windows and it works on any PC for the last 20 years? It's because there are standards like an EFI spec or the BIOS interfaces. And so we think there's value in having industry standards. And that's what the ARM64 guys have similarly said, like John Masters at Red Hat, is they want to build one image of Red Hat OS for all ARM servers. They don't want to build one for each one. So there's business efficiency, whereas maybe a Chromebook or a deeply embedded, they're okay with curating a vertical stack. Maybe. And it's a choice. That's a business choice. But key is opening stuff up so you don't get in the middle of people making these choices is kind of my view.
Will Project Treble affect that for the ARM?
So Treble, yeah, that's the shared user land on Android, and I think part of Treble is they want the one user land to work on any ARM phone.
On any hardware with that.
Yeah.
I mean, is that something that's like relevant?
No, I think that's.
Server OSs too, or just?
No, I think.
Because it's hardware abstraction, right?
Yeah. So that's a good question actually. So the Treble is a common user land for all Android phones, and they hide the HAL specific details of the Android. In the EFI world, the way it happens is you want this OS to be a common binary for any guy that says he does this standard. Because Windows, if you go to like a Windows download page, they don't say, give me the Dell version of Windows, the HP. So Treble kind of abdicated and said the bottom half of the OS in the Android world is too jacked up. Let everyone be different. But all our cool userland software, make that the same. And in fact, one of the things we'd love to do, because the concept of treble and fragmentation, everybody has that. And so in the world I live in, the CDK2 world, since everybody clones this code locally and changes it, if you look at the master upstream of EDK2 and drop a label on it and build it, it's not going to match anyone's machine in the world, right? Because they've all branched and forked. And we'd love to have a world where this code could be generic. We could treblize our EFI and say, this network stack for EFI, you just use it. It's platform independent. But today we have our own fragmentation. Everybody fragments. It's kind of the victim of success. But that's the micro world of how we manage the firmware underneath. The reason people like standards is, again, a single OS binary. That's really what's made the PC the success it has.
So the FSP layer, is that what people are referring to when they're talking about the management engine?
No. Yeah, so the management engine is essentially a separate microprocessor in our thing called our PCH. The code for it happens to live in the same storage container, the flash part, as the BIOS, but it's an independent subsystem. And when the BIOS boots up, it chats with it a little and says, hey, management engine, you can have this part of memory for yourself, here's some information, but it's like a separate computer underneath the main computer.
But the FSP is the code that enables it, right? So
Yeah.
Purism as a vendor, they have the source for FSP, they've modified FSP to not enable management engine for their version of it.
I don't know what Purism's done, to be honest.
Yeah, like them and System 76 were trying to like disable the management engine. There was like a whole
And we think
people
that
got
this,
excited about it like 6 months ago, but I didn't.
and we think it'd be great if this recipe we had, we could talk to those guys and say, could you use it? So we think what they're doing is great because they're giving people choice. Yeah. So, but yeah, there's other business reasons why we have lots of things happening there, and yeah. So that's other parts of the company. But yeah, so yeah, this part of the stack is really the inside baseball on how you build just the basic image. By the time you get to the end of the boot, when you see the bootloader, the OS guys don't know how this thing was all put together. The problem is, because of security concerns, and we have a website where we journal all of our bugs we fix, how do you know that the version of source code your machine was built on is the latest patched version? And that's why a lot of people are sweating, wanting to introspect what's in here. And then the ME even more so, because this one you could at least scrape it and the hashes and go to virus total and see. Some of these other microcontrollers, you can't introspect easily. So That's why a lot of folks are sweating these days of. And then people used to tell me before, oh, this is so complicated, the hackers will never figure it out. And I thought, oh no, don't say that. They're probably smarter than we are sometimes. And I said that about ACPI, and then Luke DeFloit did his attacks. And no, I mean, assume they know everything. And yeah.
These days, Intel gives training on how to use it.
Potentially, yeah.
B-sides.
Oh, the B-side, you're right, yes. Yeah, we do train. So yeah, so this is really reiterating what I said here. And again, this min stuff is more the fact that we're trying to just give out the subset on the web to build a minimum viable product. Not much more than that. So that's client and IoT. The big challenge now is servers. So there's this project called Open Compute, where all this started by Facebook, where the server vendors are saying, hey, you can build a server, here are the schematics, here's the diagrams for the rack, here's power supply specs. So we're participating with those guys to say, can we have a recipe to build a server out of pieces all on the web? This is taking a bit longer. We post our FSPs publicly. We have a separate repository we started for all that platform code. So TNO core here is our core. That's our 2 million lines of code. That's a generic UEFI core, network stack, secure boot, capsule update, everything that's independent of a platform. Cross compiles to x86 and ARM. And then to build platforms, Lenaro's put some platform source code up there, Intel has. So you can sort of, for an Intel recipe, you take an open source core, you take some of this platform code, and then see if there's an FSP for it. So you get your IP magic, your open source board stuff, and an open source core. And then you can do a similar recipe with core boot. Take core boot, mix in an FSP, and then we're looking to do something similar with servers here. And we have an initial server posting here. But again, the first thing is, even though blobs or opaque binaries are a little odious, we'd like to have all source all the time. Make all the pieces public so that you can build a product from the internet versus having to sign a bunch of NDAs. And here's just a little more detail from the web. Again, we have an open source work stream with, a work stream with the Open Compute project. It's called Open System Firmware. And we took a Microsoft board from Azure that they contributed the design to OCP. And we've put up enough binary pieces and source code that you can actually build a bootable image off the web. And then so we did the FSPs, but we had this 6-page restricted use license that said if you use this FSP, give us your firstborn child and other stuff, I don't remember. But and so people couldn't take the binaries and check them in their own repositories. So at the time, there was a co-pending issue with microcode. You couldn't check microcode blobs into the Linux distros like Debian and stuff. So when that happened, we asked, could we have the FSP relicense such that you could just take the blob and do what you wanted with it? And so now the core boot community, the Linux boot, can take these FSPs and check them in. As Lee asked me before the talk, there was a recent Fornix article saying about open sourcing the FSPs. That's definitely a desire to have everything open, but that's sort of not where we're at today. And speaking of where we're at today, the tools, so there's also tools when you get these blobs and source code, program fuses, do other magical things with our hardware. The complete set of those aren't open, so this open workflow where you can pull everything off the web, if you don't have the tools to finalize programming your hardware, it's not there. The FSP itself, I kind of call it, or someone on the web was calling it a soft lockdown, meaning it's not cryptographically signed, and people can build their own, but it's not open. So, you can go the path of the ARM guys, those boot ROMs I talked about. Those things are signed by the SoC, they turn on the hardware, and the OEM doesn't get to run code until memory is turned on in the fabric. We could go that path, or we can liberate the code. I think liberating is a little better, give people choice. And then documentation. One of the challenges we have is we'd like to have the documentation out there, or we're supposed to before we open source, and things like our engineering design specs. And those have not been as timely as our software development manual. So if there's a new instruction coming, the software development manual, Intel will publish 18 months ahead of time so the Linux community can upstream the kernel changes. These documents for the platform specific stuff, that platform code I mentioned, these documents often don't get posted until we ship the first product. But if you want to work with an open source community, they want to do development in the open. So we need to move some of the documentation left. And then finally, if you do give binaries to people, how do they debug it? Right? It's fine to say I'm protecting my IP, but if the magic doesn't work, how do people debug the magic? And so we have, like FSP, we have some things called postcodes that we document. We have some handoff blocks, but it's definitely not as seamless as having source code. And then finally, that Chinese menu thing I showed, this is how things get so complicated in the BIOS world. The top picture is that sort of EFI picture. We have our industry standards that tell us the different phases of initialization. If you go to UEFI.org, you'll find docs that talk about BDS, Dixie. Some people do core boot, like a Chromebook. And then now the cloud guys are doing this, this Linux boot thing. And so putting Linux in the flash. And so, you know, being open allows people to make these choices on their own. And then probably the path to openness, which we really want to aspire towards, is we're kind of in the middle, tacking towards here, I guess, second to the final one, where we open source platform code, open sourced our core, and then that FSP, can we break that out even more to something we call an SDK? Because if you look inside the FSP, it's really just our PEI phase, and it uses a lot of open source core code. So get down to the few binaries that we have to keep closed, or the request we keep closed. And then the final stage is those few binaries we pop open. And so we're probably right here, the fourth of all 5 phases. I'm embarrassed to say I think I did this picture in 2014 or 15, so I might not be the guy driving the last one because it's not going so fast, but that's at least where we're trying to go. And then, again, keep it simple, less code, more composable, min platform FSPs, put more of it on the web, and then security, put tests out there. And then looks like I didn't have a page on capsules, and I think the reason I didn't is there was a separate session at OSFC on Capsule update, but security, putting, again, tools like ChipSec, all our security features in open source, and then the Capsule update really servicing, working with the industry to make it easier to pass firmware updates. And some of the luck or good progress we've had on firmware updates are through Windows Update now, you can build one of these capsules, and it can be, and the OEMs can send it through Windows Update. And in the past, they'd have to run their proprietary tools on each PC. And so now the ecosystem can send their BIOS updates directly through Windows Update. And for Linux, there's a service called LVFS. And I think on Dell and Lenovo machines, you can get firmware updates through Ubuntu, Fedora, and AMI. Oh, great. So really what we're trying to do there is reduce the friction for the OEMs to push the BIOS updates. And then in a even bigger world, like your treble comment, today when they do BIOS updates, the board manufacturer bundles everything together and sends it because they're afraid if you update one thing outside of another, it might not work. Work with the industry to say, hey, maybe you could update parts of the firmware, like say microcode, and not the whole BIOS itself or just the network stack or the EFI core or treble-like components. So we're trying to lay the technology to make that possible, but it's obviously a business concern that if I'm an OEM and say the hardware vendor sent an update just to microcode and it didn't work, who are you going to call? Yeah, so it's not Ghostbusters, it's probably the OEM. So it's not even a relevant connection joke. But yeah, so we're trying, and yeah, and so really the reason to give talks like this is to just show what Intel's doing, saying we're open to feedback and questions. You had Paul and others on where we're trying to go, and then maybe some best practices, like on the Capsule update and servicing. I think some guys at NYU, I gave this talk to them, and they pointed me at another project where people were working on something like this, and that's great. Because I'm always the view of firmware is if you don't invent things specifically for firmware, because the firmware community is maybe 5,000 or 6,000 people, and you're not going to engineer a lot of solutions directly for them. Leverage what other people have done that's better. Like EFI, we use FAT file system, the PE, COF. Our network boot is the IETF standards, now moved to HTTP, because the big OS world invented stuff and got it right. Maybe we can curate pieces of that for the firmware workflows. So if there's something good going on out there that we could apply to this domain, always open to that feedback. But yeah, that's oh my gosh, I have a lot of references here. I must have been couldn't sleep on my flight over there. So yeah, we talk a lot about this stuff, and maybe that's part of the challenge. That's the that's definitely not in spirit of simplicity, but we got some more information, and then of course my legal disclaimer, because I work at a large company.
Are these slides online?
Yes, yeah, the PowerPoint isn't, but the PDF is.
I'll also look for the slides for the rest.
Okay. And yeah, any questions, comments? You guys all love the PC experience and EFI and Intel? I guess so. Sure.
Sure. So from an outsider perspective, like the OS and application level of open source software over all these years it's like open source has kind of won almost. You could say that, especially in the server space. But in the firmware space, in the low-level hardware space, there really are intellectual property things that not just the lawyers, you just really don't want somebody in China to make a knockoff Intel processor. Like, how much code does that really boil down to in the end? How big do those blobs really need to be?
Yeah, it's a good.
How far can you go?
It's a good question. So one reason, for example, probably the poster child for the FSP binary, and that blob is now several hundred K, is like DRAM initialization. And when you look at the DRAM initialization, if you read the JEDEC spec, which tells you how to build DRAM, a lot of these idioms everybody does, but some of the parts that maybe we do on how we train our PHY, the analog interfaces, and a lot of that's done in firmware, not hardware. So that may be something Intel worries about because it's not hidden in hardware. So on our Quark platform, that's all open source, even the memory in it, the guy who drove that told me he was able to get it all open source because the training engine was in hardware. And so they didn't have to expose it. But it's point solutions like that. And over time, I think you get there and you tell people what is the real concern. And I always say, like, about China and people copying, it's an unencrypted macro code blob. You think if they want to know, they're not running it through IDA?
Yeah.
No, if you really care, you encrypt it and only run it out of an internal memory and never do a bus cycle. And none of the BIOS stuff does that. So I'd argue in the limit, nothing in the BIOS space. But it takes time.
Yeah.
But yeah, I think the other stuff is more. People already are already sensitive to that problem and address it. That's a good question though. But yeah, it just takes time, and yeah, I think the challenge with hardware versus OSs and apps are that Linux kernel can run everywhere. If I'm talking about the code to run on your laptop or this one, the collection of targets is small. So it's not like the effort doesn't get amortized everywhere. The code to make this hardware light up on this board, you only apply to this small thing. So you don't get the economic scaling of the community as much. Whereas a web browser runs everywhere.
Yeah.
I just don't, so in other words, I don't think enough people care, right? But I think there's enough business reasons why there's value, and that's the way to position it to management, is to say, these are business reasons. And I think security, making people go faster. I think some people tell me open source is great. It's a great way to recruit, right? People who work in the community, there's your employee.next. So I think there's a lot of value to being open. And if your business value is people don't understand how your thing works, or they don't have the magic access to the magic dock, I don't think that's should be the most competitive thing. So that takes time. And for each person who says open source is great, there's business stakeholders and legal, and it's negotiation. But, all right. So thanks, guys. If no one got a camera cover, I think there are 4 more. You can be a Nirvana camera covered person.